Welcome to this explainer. Today we're going to do something really special. We're going to slow down, take a deep breath, and intuitively rebuild our entire understanding of the mathematical universe. We are definitely not going to rush through formulas or rely on blind memorization here. Instead, we're building this universe from the ground up, looking at the deep intuition behind exactly why numbers work the way they do.
Okay, let's dive right in by pausing on a truly fundamental, maybe even slightly provocative question. What actually is a number? For a lot of us, math class basically trained us to just memorize rules, crunch the numbers, and pass a test, right? But to really deeply grasp math, we need to shift our mindset completely away from that rote memorization. We have to view numbers not just as abstract, meaningless symbols on a chalkboard, but as a logical, highly connected system that perfectly describes the physical reality around us. So let's start at the very beginning and see how this builds our spatial number line step by step. Imagine the very first numbers humans ever needed. 1, 2, 3. These are our natural numbers. They're perfect for counting apples in a basket. But what happens when that basket is completely empty? Well, that vital realization gives us 0, which expands our world into the whole numbers. And then, eventually we realize we can actually owe someone an apple, right? That pushes our number line outward in the exact opposite direction, and boom, we have our integers.
Now that brings up a really great curiosity-driven question. Why do negative numbers actually exist? I mean, they don't just exist to make high school algebra difficult. Imagine standing right at the 0 mark on our spatial number line. If positive numbers are steps forward, negative numbers are simply steps backward, past 0. It's exactly the same distance, just in a mirrored direction. And honestly, that is the deep intuition behind integers. They give our entire mathematical universe this profound sense of symmetry and physical direction.
Okay, so now we have this incredibly solid number line stretching infinitely forward and backward with our integers. But look a little closer. What lives in the massive spaces between 0 and 1? Or between 1 and 2? Are those spaces just empty, meaningless voids? Well, far from it. In fact, those gaps are hiding an absolute infinity of their own.
To fill in those gaps, we use rational numbers. And actually, the word rational here comes directly from the word ratio. A rational number is just any number you can perfectly express as a fraction, literally a ratio of two integers, like placing 3 over 2 to get 1.5. As long as that bottom number isn't 0, these rational numbers gracefully step in to fill the infinite spaces between our solid integers.
Now, sometimes these fractions create decimals that go on forever. Take 1 divided by 3, for example, which is 0.333 repeating into infinity. But notice something important. Even though it never ends, it's completely predictable. Because we know exactly what comes next, it is beautifully rational. But contrast that with other decimals, ones that are basically a chaotic storm of numbers, continuing forever and ever without any pattern at all. And what's really fascinating about this is how absolutely terrified the ancient Greeks were when they first discovered these chaotic, patternless numbers. Seriously, they believed the world of numbers was built on this divine, predictable perfection. So the idea of a number extending forever with 0 predictability, it completely broke their understanding of the universe. Today, we call these terrifying entities irrational numbers. An irrational number cannot ever be written as a simple, clean fraction of two integers. Its decimal expands into infinity without ever terminating and without ever repeating a single pattern. It is pure mathematical chaos. But don't let the word irrational fool you into thinking they're just some abstract illusion. Despite their chaos, they are extremely real. Just think about the square root of 2. It starts out as 1.4142, and then the digits just scramble onward into infinity. Mathematicians have actually used supercomputers to calculate these types of numbers out to trillions of decimal places, and they remain entirely random. So literally, no matter how precise your calculator is, it can never, ever show you the full infinite story of the square root of 2. But you might be wondering, how do we know it actually exists in the real world if we can't fully write it down? Well, think about this visually. If you draw a right triangle and you make the two shorter legs exactly 1 inch long, the long side, the hypotenuse, will physically measure exactly the square root of 2. That right triangle physically exists in nature, which perfectly proves that irrational numbers exist in nature too. We see this exact same thing with pi, arguably the most famous irrational number of all. Pi is 3.14159, endlessly continuing without any pattern. But the crucial takeaway here is that pi is literally just the ratio of a circle's outer edge to its width.
Because physical circles exist in the real world all around us, we know with absolute certainty that beautifully chaotic, irrational numbers like pi are completely real.
All right, now that we have our solid, rational, and irrational numbers defining reality, let's hit a mathematical wall. I want to ask you another provocative question. Can we take the square root of a negative number? Really think about the impossibility of this for a second. A square root asks, what number multiplied by itself gives us this value? But a positive times a positive is positive, and a negative times a negative is also positive. There seems to be absolutely no way to square a number and get a negative result.
And, well, in the real numbers, we can't. But mathematics is fundamentally about finding solutions. So we expand our universe by defining an entirely new dimension, the imaginary numbers. We create a fundamental unit, a lowercase italicized I, which represents the exact square root of -1. With this simple, elegant invention, a whole new world of mathematics opens up, letting us solve actual complex problems, like real-world engineering equations in quantum physics that the real numbers alone never could.
Section 1. The DNA of math. Prime numbers. So we've explored the massive, sprawling taxonomy of numbers. Now we're zooming into number theory, which means we have to look at the very atoms of math. A prime number is a number that can only be perfectly divided by the number 1 and by itself. Numbers like 2, 3, 5, and 7. Think of them as the unbreakable fundamental building blocks of the mathematical universe. You can't snap a prime number in half and get smaller whole numbers. They are quite literally the base elements on the mathematical periodic table.
And this brings us to one of the absolute coolest concepts in this explainer, the fundamental theorem of arithmetic. This theorem states that absolutely every single whole number can be factored or broken down into a completely unique set of prime numbers. It basically means every number you can possibly imagine has its own distinct prime fingerprint.
Let's actually walk through this step by step so you can really visualize the logic here. Let's take the number 12. Step 1. Using basic divisibility rules. We know 12 ends in an even number, so it easily breaks down into 6 times 2. We know 2 is a prime, so that piece is locked in. Step 2. We break the 6 down into 3 times 2. Now both 3 and 2 are prime. So step 3. We are left with our basic building blocks. The unique prime DNA for 12 is 3, 2, and 2, and no other number in the universe shares that exact combination.
Which leads directly to a massive question. If primes are the building blocks of all numbers, how many prime numbers are there, really? And this isn't just a modern question. A brilliant number theorist named Euclid looked at these numbers roughly 2,000 years ago and asked this exact same thing. Does the list of primes eventually stop, or does it go on forever?
Euclid didn't just guess. He proved it using visual, logical reasoning known as proof by contradiction. He basically said, okay, let's assume for a second that there is a finite number of primes that the list eventually stops. Through formal mathematical logic, he showed that this assumption inherently breaks the rules of math, proving beyond a shadow of a doubt that the number of primes is infinitely large. There's always a new prime number waiting to be discovered out there.
Now, it's pretty easy to look at Euclid and his 2,000-year-old proofs and think, okay, that's a really fun abstract puzzle, but what does it actually have to do with me? For a long time, people thought number theory was just for mathematicians who loved asking theoretical questions. But how does this ancient abstract math connect to our modern daily lives in the 21st century?
Well, the answer might actually surprise you. Today, number theory is actively used to solve incredibly complex technological problems. Those ancient prime numbers are currently protecting large-scale business networks and securing our digital computer encryption. Every single time you buy something online or send a secure message, prime numbers are working silently behind the scenes. Here is the intuitive logic of how that actually works. Remember how every number has a unique prime fingerprint? In modern encryption, the digital key to a business's private network is the prime factorization of an absolutely massive number. The reason this creates a perfect digital lock is that while it's incredibly easy for a computer to multiply 2 giant prime numbers together, it is virtually impossible to look at the massive result and untangle it to figure out which primes were used to build it.
It's honestly a beautiful full circle moment. The ancient, infinite building blocks of the universe are the exact same tools we use to secure our modern digital world. So I want to leave you with a final thought to cap off our deep dive into the math universe. Since Euclid proved that prime numbers are completely infinite, what massive, completely undiscovered mathematical secrets are waiting out there in the dark, securing our digital universe right now? Welcome to The Explainer. Today, we're taking foundational mathematics and transforming it from a rigid, abstract set of rules into a deeply intuitive toolkit. We're totally ditching blind memorization today. Instead, we're going to slow down and clearly unpack the underlying logic of this math, so you can actually use it to decode the physical universe. Okay, let's dive right in.
Before we even look at a single formula, we've got to start by asking the most basic question. Why does physics rely so heavily on mathematics in the first place? Well, it's because math is literally the fundamental language of reality. You simply can't understand motion, energy, or forces through just words alone. We need a precise way to measure, predict, and quantify the changes happening all around us. Math gives us the exact instruments we need to actually read the universe.
But, before we crack open that mathematical toolbox, our source material offers a really grounding reminder. The instructor emphasizes that, yes, you absolutely must take ultimate responsibility for building your career and mastering these complex subjects. But you shouldn't run so fast after academic or financial success that you leave behind the family and friends you're working so hard for. It's a brilliant, sobering reminder that keeping a positive, balanced mindset is absolutely crucial for your intense learning journey. So, with that grounded perspective in mind, let's open up our toolkit.
Section 1. Decoding Trigonometry Basics.
I know. A lot of people panic when they hear the word trigonometry. They immediately think of endless, confusing tables of numbers. But really, it's just the geometry of finding missing pieces when you only have partial information. Our source uses a fantastic real-world analogy for this. Picture a clever thief planning to bypass a building's security. During the day, he can easily pace out the distance from the street to the bottom of the wall, right? That's his base distance. But obviously, he can't just climb up the wall in broad daylight to measure how tall his custom ladder needs to be. Here's where trig saves the day. If he knows that base distance and he can just look up and estimate the angle to the window, trigonometry becomes his secret weapon. With just one side and one angle, he can calculate the exact length of the ladder, the hypotenuse, that he needs for the heist.
So how do we actually pull off that calculation? Well, to find those missing pieces of the physical world, we divide the sides of a right-angle triangle to create fundamental ratios. You don't need to memorize a massive list of abstract concepts, just 3 basic relationships. Sine, which compares the perpendicular height to the hypotenuse, cosine, which compares the base to the hypotenuse, and tangent, which compares the perpendicular height directly to the base. Depending on which pieces of the puzzle you have in your hands and which one you're trying to find, you simply pick the ratio that fits.
But hey, in the real world of physics, things don't just sit perfectly still in neat little triangles, do they? Objects rotate and spin in full circles. When the angles in our physical systems rotate beyond 90 degrees, we move into different quadrants of a circle. To handle this, we use the ASTC rule, often remembered as all school to college, to intuitively track which of those ratios stay positive as things spin around. In the first quadrant, all are positive. In the second, only sine. In the third, only tangent. And in the fourth, only cosine. It's a perfectly logical, visual system for mapping rotational physics.
Moving on to Section 2, Reading the Terrain with Graphs and Slopes.
All right, now that we've got static shapes down, let's zoom out to see how things actually change over time. We do this by reading the terrain using graphs. Graphs are essentially just visual stories of how 2 different things interact, like how far a car travels as the seconds tick by on a clock. The absolute crucial point here is understanding slope. The core concept of decoding any linear graph is this idea of steepness. It simply tells us the rate at which our vertical variable, the y-axis, is changing relative to our horizontal variable, the x-axis. Mathematically, it's just the change in y divided by the change in x. If y is distance and x is time, boom, your slope is exactly your velocity.
And the best part is, we can read this instantly just by looking at it. Visually, a rising line means both variables are increasing together. As time goes forward, distance goes up. That's a positive slope. A falling line gives us a negative slope, meaning as time moves forward, the other variable is decreasing. And a perfectly flat horizontal line, that means absolutely zero change is happening. You're just standing entirely still.
Which brings us to Section 3. Differentiation, or, as I like to call it, the microscope.
Okay, but here's the catch. What happens when the physical hill isn't perfectly straight? What if it's a dynamic curve with a steepness that is constantly changing? You can't just take a simple change in y over a simple change in x anymore, because the steepness is different at every single millimeter of that curve. That brings us to our third and, honestly, incredibly powerful tool, differentiation. People get so intimidated by calculus, but intuitively, differentiation just acts as a mathematical microscope. Imagine looking at the curved edge of a circle. If you zoom in close enough, that tiny little segment of the curve actually looks perfectly straight. Differentiation is basically the math of zooming in on a curve until it appears straight, letting us find the exact instantaneous slope at one single frozen moment in time.
So to actually do this, we take our good old traditional slope formula, the change in y over the change in x, and we visually shrink the gap between our two measurement points. We shrink it down smaller and smaller until the gap is infinitely small. Instead of a large measurable delta y over delta x, we call this infinitely small microscopic change dy over dx. It's literally the exact same logic as a basic slope, just applied to a microscopically tiny sliver of reality.
Thankfully, we don't have to draw microscopic triangles every single time we do physics. That would be a nightmare. We have logical shortcuts. The most common one is the power rule. It's this simple, elegant formula. If you have an equation with an exponent, you just bring that power down to the front to multiply and then subtract 1 from the remaining power. Just like that. If you're given an equation for an object's curved path over time, you can instantly calculate its exact, instantaneous velocity at any given split second.
And that leads us perfectly into Section 4, Integration, getting the big picture.
So if differentiation is zooming in and slicing things apart, what if we want to do the exact reverse? Well, that's called integration. When you have a complex, non-uniform graph and you need to find the total accumulated value, like, say, the total distance traveled over a road trip with constantly changing speeds, you need to find the area under that curve. Integration lets us do this by mathematically slicing the area into an infinite number of incredibly tiny vertical rectangles, and then seamlessly gluing them all back up into one total sum.
Honestly, you can just think of these two tools as absolute opposites, functioning together as a perfect system. Differentiation takes a system and breaks it down, slicing the curve to find the immediate, instantaneous rate of change. It takes distance and gives you velocity. Integration, on the flip side, glues those infinite slices back together to find the total physical accumulation. It takes a changing velocity and builds it up to tell you your total physical displacement.
And because they're opposites, the basic math perfectly reflects that. The power rule for integration mathematically reverses the differentiation process we literally just learned. Instead of subtracting from the exponent and multiplying, we do the exact opposite. We add 1 to the power, and then we divide by that new power. The mathematical symmetry here is just beautiful, really.
So, looking back at our source material, the main takeaway is this. If you focus your energy on truly grasping the intuition, the why, behind just these 4 specific pillars, the complex mathematics of physics will suddenly feel entirely manageable. You've got trigonometry to find missing static distances, slopes to understand uniform rates of change, differentiation to microscope in on instantaneous change, and integration to zoom out and accumulate total areas. That right there is your complete foundational toolkit.
So as you step back into the real world today, I want you to look at the motion happening all around you. Look at a car braking at a red light, a ball thrown up in the air, or a pendulum swinging on a clock. Ask yourself, are you seeing simple linear changes with a constant slope? Or are you witnessing the beautiful, complex, dynamic curves that require a true physicist's toolkit to decode?
Welcome back to The Explainer. If you're feeling a bit overwhelmed by a math backlog, or if the very words set theory make you want to run for the hills, you are in exactly the right place. Today we're going to catch up and we're going to do it with total confidence. I promise you, by the end of this explainer, set theory is going to feel, well, completely natural.
Seriously, let's just take a deep breath. Math is absolutely not about memorizing a giant wall of scary symbols. It's really just about logical connected patterns. So today, we're tossing out those intimidating formulas and swapping them for simple, real-world analogies. We are building your intuition from the ground up, step by step.
Section 1. What exactly is a set? Let's take this nice and slow and set the stage for visual reasoning, rather than just abstract rules.
You know what's really interesting about this definition? It's literally so simple. A set is just a well-defined collection of distinct objects. Honestly, just think of a set as a regular physical bag. You can put items into this bag, but here's the catch. Every single item in there has to be completely distinct. If you try to drop a duplicate item in, the bag just kind of ignores it. And because everything is just floating around inside, the order doesn't matter at all. A bag with a red, yellow, and green block, it's exactly the same bag as one with a green, red, and yellow block.
So the absolutely crucial rule here is well-defined. But what does that actually mean in plain English? It just means we have to know exactly what is allowed inside our bag and what isn't. Everyone has to agree. Take the months of the year. That's perfectly well-defined, right? If I hand you April, we all agree for sure it goes in the bag. But what about a bag labeled beautiful flowers? That is not well defined. I might think a sunflower is gorgeous, but you might totally disagree. Since it relies on personal opinion and subjectivity, it can't be a proper mathematical set.
Okay, but this brings up a really interesting question. If a set is basically just a conceptual bag holding distinct, well-defined things, how do we actually write down what's inside our bag so other people know what we're talking about?
Section 2, Roster versus Set Builder Notation. Understanding the difference between these two forms is honestly where so many students get stuck.
And here is where we see the difference. First, we have roster form. This is the most direct, straightforward approach. You literally just list out every single item inside curly brackets, separated by commas, like the set of 2, 4, 6, and 8. Simple, right? But then we have set builder form. Here, instead of listing every item, you state the rule or the specific property that the items must have to get into the bag, like x such that x is an even number between 0 and 10. Now, these aren't different types of math. They are literally just two different languages describing the exact same underlying concept.
So, you might be thinking, why overcomplicate things? Why not just list everything out in roster form all the time? Well, what happens if our bag has an infinite number of items? Think about the set of all whole numbers greater than 5. If we tried to actually list them, we'd write 6, 7, 8, 9, and we'd be writing forever. Our hands would literally fall off. We desperately need a better way.
And that is exactly why set builder notation exists. It's such an elegant tool. Let's walk through the logic step by step. First, you spot the pattern of your collection. Second, you introduce a variable, usually x, to represent any potential item. And third, you apply a conditional, filter, which is usually written as a vertical bar or sometimes a colon. Think of that vertical bar like a really strict bouncer at an exclusive club. The variable x walks up, but the bouncer only lets x inside the set if it meets the exact rule we've laid out.
Let's look at a specific pattern from our sources to really cement this. Imagine a set with the numbers 2, 4, 8, 16, and 32. Okay, we can spot the pattern there. They're all powers of 2. Now look at how set builder form handles this. It elegantly says our set contains elements where x equals 2 to the power of n, given the rule that n is a natural number from 1 to 5. Take a second to really absorb that. Instead of manually listing all those powers of 2, set builder simply handed the bouncer a formula. It's brilliant.
Section 3, Empty and Singleton Sets. Now let's look at the logical differences of sets based purely on their size.
First up, the singleton set. Honestly, this definition is as intuitive as it gets. A singleton set is just a set containing exactly one element. Tying it back to our real-world analogy, it's simply a bag that has exactly one single item inside it. For example, a bag containing just the number 5.
Next, we have the empty set. You might also hear it called the null set or the void set. This is a set containing exactly 0 elements, and we denote it by that circle with a slash through it, or just a pair of empty curly brackets. Again, going back to our analogy, this is just an empty bag. It exists perfectly well as a container, but there's absolutely nothing inside it. And here's a super fascinating mathematical quirk. The empty set is actually considered a subset of every single possible set. Why? Because there's literally nothing in it to violate any rules. Kinda mind-blowing, right?
Now, I want to pause here because this specific comparison addresses a massive point of confusion. Look closely at the difference. The empty set is a bag with absolutely nothing in it. But a set containing the number 0, those are absolutely not the same thing. The number 0 is an actual mathematical item. A bag holding the number 0 has one item in it, making it a singleton set. That is totally different from true emptiness. 0 is something, emptiness is nothing.
Okay, so we have all these different bags now. Some are infinite, some are empty, some have really specific rules. But how do we actually visualize these different bags interacting with each other? How do we see the overlaps?
Section 4, Visualizing Sets with Shapes. Let's map all this abstract math right into physical visual space.
To do this, we distill all that logic into simple shapes. We use a large rectangle to represent the universal set. This is the grand universe of everything we actually care about in our current problem, like, say, an entire school of students. Inside that universe, we draw circles to represent our specific sets. Circle A might be students who play cricket. Circle B might be students who play football. Doing this immediately gives us a bird's-eye view of how our sets exist within a much larger universe.
And this completely clarifies how the physical space of the diagram defines relationships. Think of these as geographical regions on a map. See the overlapping region in the middle? That's the intersection. Those are elements shared by both sets,
like students who play both cricket and football. What about the individual circle area that doesn't overlap? That represents elements unique to one set, students who only play cricket. And finally, the space outside the circles, but still inside the rectangle. That's the complement. Those are elements in our universal school, but in neither sports subset. Basically, the students who just don't like sports at all.
Just take a step back and look at that. Mathematics really is just logical, connected, and intuitive patterns. By stripping away the heavy jargon and just looking at bags, bouncers, and visual map regions, you've built a deep, intuitive foundation of set theory.
Welcome to This Explainer. Today, we're acting as visual detectives to build a deep, logical intuition for solving algebraic inequalities. If you've ever felt totally bogged down trying to memorize a dozen different math rules, well, you're in exactly the right place. We're ditching rote memorization entirely. Instead, we're going to focus on the why behind the math, making these concepts feel logical, connected, and incredibly intuitive. But before we get into any formulas, I want you to hold on to this really famous and honestly highly misunderstood question. Why in the world does the inequality sign magically reverse when a negative number gets involved? Seriously, for years we're just told to memorize it. Just flip the sign. But today, we're going to prove it visually so you never have to blindly guess again. So, here's our roadmap for the scaffolded discovery approach. We're starting with the intuition behind the symbols, then visualizing the number line. After that, we'll tackle that negative sign trap, solve some linear inequalities, decode quadratics, and finally, wrap up with the wavy curve method. Let's get into it. Section 1. Intuition behind the symbols. Okay, let's look at what these abstract mathematical symbols actually represent in reality to set our foundation. Think of an equation kind of like arriving at one exact destination, right? If x equals 65, boom, there's only one correct answer. But in inequality, that represents a whole continuous region of valid answers. It's literally just like a speed limit. If the sign says speed limit 65, well, x is less than or equal to 65. Going 60, totally fine. 40, fine. But 66, yeah, that gets you a ticket. So we aren't looking for just one number anymore. We're hunting for an infinite set of numbers within a specific boundary. Let's test that intuition real quick. Which of these is true? Now, it might feel a little like a trick question, but the statement 5 is greater than or equal to 5 is completely 100% true. Why? Because that symbol means greater than or equal to. It only needs one of those conditions to be satisfied to work. Since 5 equals 5, the statement is solid. That second statement, though, 5 is strictly greater than 5, absolutely false. Moving on to Section 2, visualizing the number line. Let's take this logic and actually map it out physically. We define these regions using what's called interval notation. You can think of these sort of like fences. Square brackets mean we have a closed interval, meaning the boundary point is a valid answer and is fully included in the solution. Parentheses, on the other hand, mean open intervals. We stop just shy of the actual number, so the boundary is excluded. Oh, and a really crucial point here, we always use parentheses for infinity. Why? Well, because infinity isn't a number you can actually reach and include. This brilliantly illustrates our playing field, the trusty number line. This is where our infinite sets of answers live. When we graph these inequalities, we mark the include endpoints, the ones with that or equal to line underneath, with solid filled-in dots. For boundaries that are not included, we use open, empty circles. Having this visual map really prevents you from misinterpreting your final mathematical answer. All right, Section 3, the negative sign trap. We've reached the sudden twist in our journey, and honestly, this is where almost all the mistakes happen. Here's the deal. When you treat an inequality like a normal equation, adding or subtracting a number on both sides keeps the scale perfectly balanced. The symbol stays exactly the same. But if you multiply or divide both sides by a negative number, the whole relationship fundamentally changes, and that sign must reverse. But hey, remember my promise earlier? No rote memorization. Let's see exactly why this happens. Let's pause and actually prove this visually. Look at this simple, undeniable truth. 3 is obviously greater than 2. Makes sense, right? On a number line, 3 sits further to the right than 2. But watch closely what happens if we multiply both of those numbers by -1. 3 becomes -3, and 2 becomes -2. The numbers literally mirror across 0 on our number line. Suddenly, -3 is sitting further to the left than -2. And because it's further left, it is mathematically smaller. The direction of the inequality is inherently reversed by the geometry of the number line itself. That is exactly why the sign flips. So here is the absolutely crucial takeaway. Because multiplying by a negative flips the sign, you should never ever blindly cross-multiply a variable like x out of a denominator. Think about it. If you don't know whether x is a positive or a negative number, you literally don't know whether to flip the sign or leave it alone. It's a massive trap. Always keep your variables on one side and work your way towards 0 instead. Section 4. Solving linear inequalities. Now that we're armed with our visual rules, let's step into some actual problem solving. We solve these linear inequalities step by step, just like regular equations, by isolating the variable. But we have to strictly pause at step 2. Imagine you end up with something like negative 2x is less than 8. To isolate x, you have to divide both sides by negative 2. And that right there is your trigger. Because you divided by a negative, that less than symbol flips straight to greater than. 8 divided by negative 2 is negative 4. So your final answer is x is greater than negative 4. Then you just graph that region to visualize your true set of answers. Section 5. Decoding quadratic inequalities. Okay, time to scale up smoothly into our boss battle. Quadratics. I know they look intimidating, but they are incredibly satisfying once you see the pattern. Instead of using some messy formula, I want you to think of a factored quadratic, say x minus 4 times x plus 3, as just a simple multiplication of signs. We really just need to figure out what combination gives us the positive or negative result that the inequality is asking for. A positive times a positive, that's positive. A negative times a negative is also positive. Only a positive times a negative gives us a negative result. So our only goal is to map out where these factors change their signs. To decode this map, we go hunting for what we call critical points. These are the exact numbers that turn our individual factors into 0. So if you have the factor x minus 4, the critical point is exactly 4. Now, why do we care about that? Because 0 is the boundary line. It's the precise border where an expression flips from being positive to negative. Which brings us to section 6, the wavy curve method. Let's see how all these pieces merge into the ultimate visual shortcut, also known as sign analysis. Here's how we execute this method. First, make sure 0 is on one side and factor your quadratic. Then, you plot those critical points we just talked about right onto the number line. These points break the world up into distinct, separate regions. Next, just pick a random test number from each region, plug it back into your factors, and see if the resulting product is positive or negative. Finally, shade the regions that give you the answer the inequality demanded, either greater than 0, meaning positive, or less than 0, meaning negative. Now, there is a fantastic shortcut to notice here. It's basically a math cheat code. Let's say you have a factor that is squared, like x minus 3 squared. We call this an even multiplicity. Since any number squared becomes positive, the sign on the number line will actually bounce at the critical point of 3. It stays the exact same on both sides. But if a factor has an odd power, like just plain x minus 4 to the first power, the sign will smoothly alternate from positive to negative as it crosses the boundary. Remembering this rule will save you tons of time testing numbers. So let's recap how we moved from confusion to mastery today. We learned that inequalities are continuous regions, not just fixed points. We saw how open and closed boundaries dictate our interval notation. We proved, visually, that mirroring across 0 explains exactly why the inequality sign flips when multiplying by a negative. And finally, we saw that quadratics are easily conquered just by finding 0, plotting critical points, and mapping out the positive and negative intervals. I'm going to leave you with this final puzzle to really spark your mathematical curiosity. If you have an inequality like x squared plus 9 is greater than 0, the quadratic equation part has no real solutions, right? Because it never actually touches 0. And yet, the answer to that inequality is all real numbers. So, why might an equation with absolutely no roots hold true for every single number in the universe? Think about the shape of that graph, and I guarantee you'll find the answer. Thanks so much for joining me on this explainer, and keep questioning the math.